Many firms and many governments are in favor of more innovation. They often neglect that innovation has a direction and take for granted that innovation is good and in turn more innovation is better. For instance, when they directly compare the performance of a firm or a country, they use indicators such as R&D spending or patent count because more is assumed to be better. Against this background, there is a need for a better understanding of the nature of innovation, beyond the current view that sees innovation as either always good or always bad, because innovation can have positive and negative effects, and those positive and negative effects are typically unevenly distributed. By considering that, better innovation policies can be designed, and this is the case of a European Green Deal, which emphasizes the importance of protecting our planet from polluting industries. This paper aims at exploring inventive dynamics in the chemical industry because of its long legacy in inventing substances that have proven to be particularly harmful to ecosystems and human health. This paper builds on some of the most advanced computational chemistry tools to predict the potential hazardous impact of chemical inventions, and it is grounded on the very basic principle that patents are documents that provides information on scientific and technological advancement, and that the measurement of their toxic content offers a novel way to observe the nature and the direction of the knowledge generation of inventing entities in the chemical and in other industries. To the best of our knowledge, no existing studies link patent data to the structural properties of chemical compounds to measure their impact in terms of the potential harms to humans and ecosystems. More specifically, we introduce a three-step methodology to predict the potential toxicity of chemical patents. Step 1 involves the search and the extraction of the chemical content from chemical patents. For this, there are several databases that allow for the full-text search and large-scale extraction of the chemical content from patent documents. But independently of the source of the data, extraction of the chemical contents from patents results in a compound patent association. Step 2 involves the use of computational chemistry techniques as the quantitative structure-activity relationship models or quasar models. Quasar models are mathematical models used to predict any potentially undesirable or adverse effect of a chemical compound based on their chemical properties. Step 3 involves the aggregation of the chemical compound toxicity score at the patent level. In this video, we will illustrate three main measures of patent toxicity. First, the total count toxicity that counts the total number of compounds in the patent that can be categorized as toxic for human health or for the environment. Second, the share toxicity that is measured as the share of patent's compound that can be categorized as toxic for human health or the environment over the total number of patented compounds. Third, toxicity concentration that measures the extent to which toxicity is concentrated in one or few or can be detected equally across all the patented compounds. This measure is based on an adaptation of the Deerfindal index. We suggest that the measurement of patent toxicity may open interesting avenues for future research with potentially strong policy implications. More specifically, by measuring the toxicity of chemical compounds in patents, we can assess whether different government policies or supranational conventions have had an impact on the direction of inventions in the chemical industry. Also, by measuring patent toxicity, we can understand how, when, and under what condition companies change their patenting behavior as rumors of ban on certain chemicals surface or are implemented.